There were 6 activities that I asked you to do. 3, 4, and 5, 7, 8, 9. I don't ask you to do activity 1 and 2 because each of those would take you almost an hour each. It's awful. But here's what you would have learned in activity 1 if I did assign it. You ready? You would have learned that the inside of the cell is negative. I think I covered that already. Are we good? And you also would have learned that the inside of the cell can depolarize or hyperpolarize. I think we covered that. Check and done. We don't need an hour on that one. Then in activity 2, another hour. And here's what you would have learned, Ryan. You cannot hear through your eyes, see through your nose, smell through your mouth, or taste through your ears. That's what you would have learned. Meaning, receptors are specific for a stimulus. Pain, temperature, photons, they're specific. That's what you would have learned. Now in activity 3, here's what you're going to learn in activity 3. You're going to learn that in order for an action potential to occur, you have to reach threshold, which means the voltage-gated channels open. If you don't reach threshold, this is a graded potential. If you do reach threshold, you have an action potential which is all or none and reproducible. You're basically doing the Hodgkin-Huxley experiments that I showed you this week. As you continue activity 3, you up the stimulus, just like Hodgkin and Huxley did. Remember, they asked the question, if we give a bigger stimulus, do we get a bigger action potential? And we don't, remember? It's all or none. If you fire the bullet, it comes out with the same force, whether you're mad and you pull the trigger fast, or you're like, oh, Ryan, I like you, I'll pull the trigger slowly. Once you hit that trigger point, the bullet is fired. All or none, same intensity every time. So in activity 3, you are performing the Hodgkin and Huxley experiments. Good? All or none. Stimulus, got to reach threshold. Then after that, it's all or none. It's all or none. Okay, then activity 4. Okay, I've actually already told you about activity 4 earlier today. In activity 4, you're playing with tetrodotoxin from pufferfish and lidocaine. Lidocaine and tetrodotoxin both are sodium voltage-gated channel blockers. And that's the first gate to open in the action potential. So if you block it, you're not going to get an action potential. And as you do that experiment, what you're going to see is tetrodotoxin is much, much more potent. Meaning you're going to block the action potential a lot more rapidly than when you add lidocaine. You see, we take toxins and poisons from the environment around us. We pay attention to things that can kill other living organisms. We pay attention to that. And then we try and manipulate it so that it doesn't kill you, but gives us a benefit from it. If you have a cavity, numbing that area before we drill it out is a benefit to you. You won't have an action potential relaying the pain. Your brain won't interpret anything then. And it's not going to kill you. I would never say, okay, Sunny, you need your cavity fixed. I'm going to just give you a whole bunch of tetrodotoxin. You'll be okay with that, right? No, microgram amount can kill her. We take toxins and poisons from plants and animals. We see what they do. We ask, how can we make this safe to use, reversible, if you will, but not lethal? We manipulate this stuff all the time, which is why it is so important for us to preserve our environment. There are a lot of organisms in the rainforest we have yet to discover, plants yet to discover. Who knows what we've wiped out before we even knew it existed and what benefit it could have had. And the ocean is a similar type of environment. We're making better and better machines to go deeper and deeper, and we're discovering organisms that can live without daylight, that can use a process, a chemical process instead of photosynthesis to make energy. Who knows what we can do with that? So you don't have to be a tree hugger. But you can be a clinically invested person, and you realize we get a lot of our drugs and medication based on what other organisms around us do with it. And then we tinker with it all the time. I didn't finish the last 2 slides, but I will. One of those 2 slides from today's lecture talks about the Brazilian wandering spider. You don't like spiders, I take it. I love spiders. Spiders are good. Spiders eat the bugs that are eating my cherry tomatoes. So
I understand their necessity. I'm still terrified.
A Brazilian wandering spider can get big enough where, you see the little black trim border around here? Could you not see the black trim border from the back of the room? Now imagine a spider the size of my hand. You'd see that, wouldn't you? That's how big they can get.
That's disgusting.
Wait, there's more. They are the most lethal spider on this planet. Yes, they are. In North America, our most lethal spider is the black widow. But it is not the most lethal in the world. The Brazilian wandering spider gets that luxury. And when it bites you, it causes a lot of nitric oxide release, which I told you all about today. And that would cause profound vasodilation. Your blood pressure would tank. You wouldn't be able to pump blood to your brain. You'd die because you didn't have blood pressure. It's like anaphylactic shock, if you want to think of it that way. And men who are bitten by it show up in the morgue stiff for more than one reason. Because the corpora cavernosa uses nitric oxide to engorge with blood. So guess what pharmaceutical companies are doing with Brazilian wandering spider venom? Well, now, okay, so...
That's crazy.
Wait, let me tell you, this is real. Viagra. Remember how you learned that acetylcholine, you can get drugs that make it last longer? Okay, so Viagra is a drug that impairs the enzyme to degrade nitric oxide. So the nitric oxide lasts longer, which is why they have an erection for quite some time. So pharmaceutical companies want to do this. Tinker with the Brazilian wandering spider venom so it's safe, where you get more nitric oxide released, and combine it with Viagra so it lasts longer for a super erectile dysfunction drug. Uh-huh. No, it's not.
No, like the erection part of it.
You what?
Like an erection lasted like more than 4 hours, they tell you to call a doctor. They're trying to get like 10 hours or something. That'd be terrifying.
So,
Like,
what is it with you being terrified over these topics? That's twice now. He's like, this is scaring me.
to help with the whole, it'd be something to help with the whole.
So, for the young ones in this room that don't know how erectile dysfunction drugs work, most of the time when you take these drugs, It does not make your penis go ping! Where now you're out on a date, just like, let me get the door for you. It's not. Why, yes, we are here on the map. That's not how it works. You still have to be aroused. So it's not like immediate. That's most of the time. Can some men be very sensitive to it and that does happen to them? Yes. And that's why they say if it becomes so discomforting and for a long time, yeah, you should call. You're being exquisitely sensitive to it.
Yeah, they didn't teach us that in the commercials.
I know, that's why you're here. And then, once you have sex, it's not like after the deed, you're still like, let me get the door for you. Ping! Let me go find somebody else to poke. No, that's not how it works. So, it just augments the situation. Let's just leave it that way. Most people should not have an adverse reaction, which is why it's really important that you don't go to your buddy and say, hey, do you got a Viagra? I've always wanted to try it. And they go, why, yes, here, try this. Because there's blood work that goes along with it. Do the blood work, they're going to make sure that everything is okay with your liver, etc., and try and rule out any possibility that you might have this adverse, uncomfortable effect. So you don't want to share prescription Viagra. Plus, a lot of men don't understand that you don't need to take the whole pill. You can. A little bit goes a long way. And you got to figure out how much you need to make you go a long way. Is that better?
Yes.
Yeah. You're terrified too much. Who abused you? Is what I want. Or keeper. It's twice now. I'm terrified. What happened to you, baby boy? Okay. Now, speaking of terrified, going back to the homework assignment that I said was optional. Remember that one? Any takers? Could be fun. Yeah, seriously, tell anyone, keep the kids until next Thursday. Then again, it might lead you to another one.
Oh no, that's not happening.
Okay, good. So let me tell you in activity 5. Why, when you do activity 5, it's going to take a little bit of time, but you should be thinking, oh, this was the optional homework assignment. Absolute versus relative refractory period. Absolute refractory period, shown here in orange, means that the threshold is infinitely high and no amount of stimulus, no matter how great, is going to get that action potential to happen again. That's the homework assignment. How long do you have to wait before you can go again? Remember? You are to determine your absolute refractory period, and then you are to report back on how much extra work it takes to get you through your relative refractory period. So in this activity, you start out firing every 250 milliseconds. I'll put that in perspective. It's like saying, let's have sex every 250 hours. Arguably, you could reset and ejaculate again after 250 hours of rest. And then we cut that time in half to 125 milliseconds. And you find out, with this same stimulus, can I get an action potential? That's like saying, can I go 125 hours in between sexual activities using the same stimulus, and I am able to have an orgasm? Then you keep cutting the time in half. You keep cutting the time in half. And that means, for you all, cutting the time in half, do you have enough time to rest, to have sex again successfully with the same amount of stimulus? And what you'll see is, As we cut the time in half, eventually we have to raise the stimulus. Like, honey, can you have sex again in 30 minutes? Well, I can, but now we need the porn and the peanut butter. Honey, can we cut the time in half again to 15? Well, yes, but I need the porn, the peanut butter, and another P, the neighbor's cat.
She's getting
Excuse me.
Another pussy.
Oh, I took
A third player.
Or the neighbor, whatever you want. You get my point. We talked about this. Eventually, you cut the time down to 3.75 milliseconds, and you keep upping the stimulus. Okay, the porn, the peanut butter, the cat, the neighbor, whatever. And the whole thing times out on you. You don't know. 3.75 seconds, could it go again if I just added more stimulus? The computer program says you're done. Well, I threw my book around the room and said, I need to know, because that has a time frame of 1 millisecond. 1 millisecond, not 3.75. So at the end, I don't know, I could still be in relative refractory period, and I just need to up the stimulus. Porn, the peanut butter, the cat, the neighbor, maybe the neighbor's mom. I don't know. I don't know. They time out. So you should be very frustrated at the end of that experiment, is what I'm trying to tell you. We never know if we got into absolute refractory period, where no amount of stimulus, no matter how great, can get the action potential to happen. The threshold is infinitely high. Then, activity 6, you do not need to worry about. That's okay, we talked about it. How do we code for intensity? What's the difference between a paper cut and a scissor cut, remember? Frequency. So I didn't assign that one because I think we got that. And then we do activity 7. In activity 7, here's what you learn. Size matters, and so does myelination. That's what you learn. Size meaning the size, the diameter of the axon, right there. The bigger the axon, the faster the ions can flow through the cytoplasm to the next voltage-gated channel. And myelination helps with saltatory conduction. I showed you that in lecture 2. You do not need to memorize the equation that you will use to calculate velocity of the action potential. Just know, bigger, more myelination, faster, okay? Then in activity 8, we're at the terminal bouton. And at the terminal bouton, when the action potential arrives, a different voltage gate opens. Calcium voltage gated channels open. Calcium diffuses into the cell, causes the synaptic vesicles to fuse and exocytose the neurotransmitter. Now, if you allow more calcium in, you're going to get more neurotransmitter released. It's directly related. More calcium, more signal released. So you're going to play with two different concentrations of calcium. The higher the concentration, the more neurotransmitter released. Then in an experiment in that activity, you're going to use something similar to calcium, something that also has +2 charges, magnesium. And you're asking the question, is this an acceptable substitute? Could anything that has a +2 charge get the synaptic vesicles to fuse and exocytose? And the answer is magnesium is not an acceptable substitute. You will not get a direct relationship. It's not as good as calcium. And in fact, in Unit 3, you're going to learn about some women who, when they get pregnant, they have a complication called preeclampsia. And they get very dangerously high blood pressure. And when that happens, their neurons start firing. And they start dumping neurotransmitter. And these women, when they start having seizures, this is called eclampsia. It's very life-threatening, both to mom and fetus. So guess what we give mama to stop the seizures? Magnesium. It gums up the calcium channels. It's not an acceptable substitute. We get less neurotransmitter release, less stimulus for her skeletal muscle. She doesn't have the seizures as much anymore. So that's why magnesium is usually our first thing to go after for seizures. I'm pointing at you because of our conversations.
I was just thinking that. That's very interesting.
I told you I'd learn you a lot of things. You just gotta stick with me.
Well, some people say that they use magnesium for, not seizures, but you know how you have, I get that, when I'm stressed or something, and my eyes start to twitch or something.
That is not a seizure, but it's unwanted muscle movement.
So they would say, why don't you take some magnesium for it? And I have, and it does sometimes. That makes sense.
Okay. Next one, last one, and then you're out of here. Activity 9. In activity 9, when you do this activity, pay attention to your system you are using. Number 1, you are using a 2-neuron chain. It's hard to see, but this purple cell right here, there's its axon, that is 1 neuron. And then here is a second neuron. One is communicating to the other. You have 4 recording electrodes, R1, R2, R3, R4. R1 and R3 are inserted into the cell bodies. And this is where we have graded potentials. R2 and R4, those recording electrodes, are inserted into the axon for neuron 1 and neuron 2, respectively. That means they're detecting action potentials. If neuron 1 reaches threshold, calcium will enter the terminal luton, and it will release neurotransmitter onto the second neuron. If it begins an EPSP, the second neuron will get closer to threshold. If it reaches threshold, it will have an action potential, and then it will release neurotransmitter. And as you do this experiment, you will realize that the more you stimulate neuron 1, the more calcium comes into neuron 1, the more neurotransmitter that's released, thank you, activity 8. And that means neuron 2 reaches threshold over and over and over again, and it fires an action potential over and over and over again. So make sure you really pay attention to that one, because it takes all of the activities together and combines them all to give you the big picture. Bye. I have a question. Stop.